All right, I think let's get started. Hello, everyone. Good morning, good afternoon, or good evening, perspective to where are you? Thank you for joining us for this webinar organized by the Canadian Geotechnical Society Young Professional Committee. My name is Rajita Aratna. I am a geotechnical engineer at WSP Canada, based in St. John's, Newfoundland. And I am serving the CGS YP committee as the knowledge lead and will moderate today's webinar. We, CGS YP committee, initiated this webinar series to allow young professionals to enhance their knowledge in a range of areas of geotechnical engineering. We successfully conducted 7 webinars so far this year. So if you are interested in listening to our past talkings, recordings are available on our YouTube channel, and I will post the link in the chat later. Before we get started, there are a few housekeeping notes. To avoid any disturbance, I disable audio and video access. If you have any questions, please use the chat option. Also note that this webinar is recorded and will be available later to view on our YouTube channel. Presentation will take 40 to 45 minutes, and there will be a brief Q&A session at the end. So if you have any questions for the speakers, please type them in the chat and I will take them as they feel. Today our speaker is Carrie Murray from Stantec. Carrie is a geotechnical trenchless leader specializing in feasibility and risk assessment, design and construction of complex crossing using horizontal directional drilling, also known as HDD, direct pipe installation, microtunneling, pipe checking, and auger bore methods. She has 22 years of experience as a consulting engineer and 2 years of experience as a geotechnical lead with an HDD contractor. Her trenchless portfolio is primarily focused in Western Canada, having completed hundreds of crossing projects with several projects throughout North America and abroad. Carrie has extensive experience with geohazard, geotechnical investigations, instrumentation monitoring using near real-time technologies and remote sensing, and provides practical construction oversights. Carrie has undertaken geotechnical analysis of existing pipelines and roadways affected by landslide geohazard by developing instrumentation surveillance philosophies and remediation through stress relief, dewatering, rerouting, and trenchless methodologies. Carrie has written numerous publications related to trenchless risk and landslide assessment. She also volunteered on the education committee of the Canadian Underground Infrastructure Innovation Center, and she's also a regular presenter and technical reviewer for the North American Society for Trenchless Technology, Nordic Compressors. She contributed to the trenchless techniques for pipeline installation chapter included in the second revision of the book ASME Pipeline Geohazard Planning, Design, Construction, Operation, which was published in 2019. So you can see we have a very special experienced engineer, researcher with us today. So without further ado, I would like to invite Carrie to deliver her talk on pipeline geotechnique. Over to you, Carrie.
Great, thank you, Rajit, and hello, everyone. I'm just going to share my screen here. Rajit, it's showing up?
Yes, we can see it now.
Okay, fantastic. So welcome, everybody. Thank you for joining. I'm pleased to be invited to share a little bit about pipeline geotechnique as part of the Young Professionals Initiative to learn a little more about the geotechnical field. And I hope today there's a thing or two that's intriguing to you, and look forward to a little dialogue at the end here. So today, because the topic is quite broad, I've got the focus of the talk looking at an overview of pipeline interactions with geomaterials, highlighting geotechnical implications to pipeline integrity. And then we're going to look at considerations to reduce soil-to-pipe interaction threats in open-cut trenching, with a particular focus on landslides. And then looking at considerations to avoid obstacles or to avoid or reduce soil to pipeline interaction threats using trenchless technologies. So that's the goal for the talk here this morning, or today. So just an overview of Canada's pipeline infrastructure. So this was published in 2020. To date, in that year, there was up to 840,000 kilometers of pipelines in Canada as an estimate. So I did look it up. It would go around the moon and back with some pipe left over. So there's a lot of oil and gas infrastructure in this country. More has been built since 2020, and it gives us geotech engineers a really interesting place to practice our profession. So specifically looking at the oil and gas pipeline system, from where the oil and gas wells are started, just the schematic is to show where the pipelines would be headed to. So from the source to the refinery, and then off to the end users. So there's, this is where the big length of pipelines getting contributed from. And also not to forget that there are other buried pipelines around that aren't just oil and gas. And so the same principles apply to all pipelines, whether it's electrical conduits, telecommunication, sewer and storm lines, water infrastructure, reclaimed water, irrigation. There's even a beer pipeline in Belgium. So they have 3.2 kilometer long stretch of pipeline that heads from a brewery in the an old downtown area off to their bottling factory. So it was built in 2016. It's just a little fun fact of what you can put in a pipeline. We have the climate change actions with CO2 pipelines coming on board for carbon dioxide sequestration. There's the energy transition that's happening, so potentially hydrogen pipelines upcoming. So lots of commodities can be put into pipelines. And then looking at the life cycle, just starting right from route selection, headed into design, construction, and then operation through the design life of the pipeline. So that would involve monitoring, maintenance, mitigation at times, and then decommissioning when the asset's no longer in use. And so the geotech engineer needs to consider where our expertise fits in this process. So is this a new installation, or is this an existing pipeline and we're in the operation stage where we're doing some monitoring and mitigation support? So knowing the soil to pipe interaction is the critical outcome of what a geotechnical engineer is doing. Knowing some things about the pipeline are important. So the material type. So oil and gas pipelines would be steel, but these other utilities could also be in HDPE or PVC, so plastic pipes. There could be composite pipes that are steel with a plastic lining and variations of those. The age of the pipeline can be important. Depth of burial, the diameter, the operating temperature can be important. If there's thermal effects with its burial depth to the ambient air or the air the temperature in the ground. And then potential defects in the pipeline. So has it been affected by deformation with, is it potentially dented, buckled, wrinkled, has some ovality, like indications of strain? Corrosion and cracks can appear in steel pipelines too. And then where are the areas of the highest sensitivity? So that could be at bends, welds or tie-ins, so just different points on the pipe that might require a little more focus. And so as we are doing our work, we need to consider these things too, to help the operator know where to tailor their focus and how we can address these issues. So then the geotechnical considerations, really looking at those soil to pipe interfaces using terrain analysis, and then from that coming up with geohazard constraints, considering what the soil and groundwater conditions are, and the material properties of the soil or rock. And so these are long linear infrastructure. So, you know, we're going through a variety of terrain typically, and a variety of constraints and such. So, you know, these are, it's an important study to be addressing this and identifying, characterizing where problem areas could be. And then looking at the geomaterials and processes to maintain long-term pipeline performance. So this is really a consideration to ground behavior as it will interact with the pipeline. And so this is observed in the construction and then through operation phases, and could be different whether there's an open cut environment or like a trenchless burial that has a greater depth of cover. So then looking at the terrain analysis piece to characterize the ground conditions along the pipeline alignment, as using all kinds of different tools these days. So the ortho imagery and LiDAR and air photos and all of that work is used to pull together some mapping using GIS-based systems, where you can come up with terrain polygons that are then assigned a material type and parameters as well. And then once that process is done, the terrain analysis piece, the geohazard constraints are then mapped out. This can be a desktop level that then is ground truthed, but pulling out the constraints that need a little more focus from the pipeline designer and throughout construction, or perhaps it's remediated early in the route selection stage. This is a really important consideration. And so then making, you know, problematic areas a color code of like red to show that there's potentially landslide terrain or that sort of thing is a really important visual feature. And so LiDAR imagery has really changed the way we do business these days, and has popped out these geohazard constraints for us in really obvious way. I remember in undergrad taking terrain analysis with Carl Sauer at the University of Saskatchewan, and his whole goal of that full year course was using stereoscopes and air photos was to identify landslides. And so we didn't have the opportunity to use LiDAR back then, but you know, now it pops out so dramatically, and we see like the you know, the satellite imagery compared to LiDAR, and then we can pull out like different features that could be important to a pipeline right away. So on the lower left, like seeing the vegetated slope in the satellite imagery just really pops out to show a landslide on this little river valley, and in all the undulating topography. So looking at these images is a really important step. And also to not narrow your focus to just the right of way for a pipeline. You know, there's the pipeline owner will get a narrow strip of land so that the pipeline can be constructed and maintained. So, you know, can be a few meters to 50 meters kind of thing. And so when we are doing our terrain assessment and characterizing landforms and materials, our inspection needs to go a little further beyond that. So when you're obtaining LiDAR and imagery, that's something to keep in mind, that, you know, if there's something going on outside of the right-of-way that could in time affect the right-of-way, it's something that needs to be identified up front so that it can be addressed. So then looking a little further at geohazard constraints, right at the routing stage to assess pipeline risk, it can be an opportunity to reroute the pipeline if we're early enough in design that, you know, that something, this is showing a river crossing and there's a big landslide slope off to the right that's colored in red and orange. And so if, you know, an initial design was going through a highly active area or potentially considering trenching up a valley slope, this is the opportunity to say, to avoid this, either with a reroute or like lowering the line and doing a trenchless crossing. So perhaps a horizontal directional drill as shown here in the bottom image, so that the threat could be eliminated, so that you totally avoid that feature. So then looking at the soil pipeline interfaces, what ground conditions would result in high construction costs or high maintenance costs? And this is where geotechnical engineers could really provide value to the owner. And so early identification, assessing and mitigating these is the goal. So what is the groundwater level? Is it within trench depth for the pipeline? Will dewatering be a big issue? Is the pipeline ascending a steep slope? What are the issues there related to rockfall and safe excavation, construction and entry? And then like a big landslide. So this is showing the lower left image showing a big, a high headscarp of a landslide. Is it active? Can it be avoided? Or like cobbly terrain too. So some tills are particularly cobbly, and, you know, identifying them in our desktop terrain mapping as a moraine or a till is usually considered a favorable pipeline construction situation, unless you're in a bouldery, cobbly kind of till. And then there's a lot of extra construction cost with getting rid of the bigger clasts and trying to get sand bedding in so that there isn't this point loading of the pipeline on these bigger rocks and boulders. So there's a whole host of situations that could affect the either the pipeline construction or its long-term operation, and that's where we get hired to help out. And then the list is kind of here, and it's not exhaustive, but just to, as the terrain mapping is identifying wetlands and landslides and through mountainous terrain, glacial marine clays affecting Quebec or the coast of BC in the north, that cobbly moraine, as I said, permafrost, fault seismicity, any of those terrain units will have sensitivities to the pipeline. Weather-related interfaces too, so construction seasons and related to like big storm events or erosion and those kind of considerations can really have a driver on cost and how the ground will behave under those big weather events. The right-of-way configuration too plays a really big role in how the pipeline interacts with these terrain units. And so there are situations often that arise where you can't put the pipeline exactly where you want it, and you're forced to run in a certain orientation on a landslide or a ridge crest or those such things. And so there's a couple of schematics here that just highlight then what construction could look like and with the situations that that could arise from that. So stockpiling soils on slopes and excavation entry, safety measures, and slope stability, groundwater, all of those things is something that that we need to consider. So then looking at the soil properties, those themselves, they are required by the geotechnical engineers to be used for pipeline stress analysis. And I guess where these are used as the pipe stress engineer will run this analysis at design when the pipeline has been as-built after construction, and then in special conditions such as during the maintenance phase, so in integrity digs or perhaps a pipe stress relief due to landslide movement. So there's some key points to make here that generally in a trenched excavation, a shallow burial of pipeline, we're in this low stress regime. So consideration to soil mechanics in this lower stress environment is required. So for example, if in your minds you can recall the stress strain curve, it is non-linear in the low stress regime. So it will give you a higher strength, so higher friction angle and no or little cohesion. So the parameters that are provided are not conventional to what we would typically do in like for foundation projects, for example. So this specific area does require some extra reading by us classical geotech practitioners. And Jim Oswell has basically written a book on this. He literally has. It's called Soil Mechanics for Pipeline Stress Analysis. He's got the second edition out in 2020. And so I would encourage you to read that and reach out to the other professionals that are working in this field, because it is slightly nuanced and needs some special consideration. So taking a look at landslides specifically as a geohazard to pipelines, I have a susceptibility map of Canada up here for landslides, and the red is showing, red and orange is high susceptibility. So, oops, sorry everybody, I clicked the wrong thing here. So we're seeing where there's population in Quebec, Ontario, and all through Eastern Canada along the ridge, there's high susceptibility to landslides, and then all through the prairies and into BC because of the steeper slopes and the interior plains region here. And coincidentally, most of the oil and gas pipelines sit in this area of the interior plains because of the geological setting there. So they are an important consideration and something we'll spend a little bit of time talking about. Because if a landslide movement happens and interacts with the pipeline, there is a pretty high consequence of a spill due to loss of containment. Costs then become really high. There's environmental and social costs, and oil and gas pipeline operators are doing what they can to safeguard their pipes, which requires a geohazard management program where we get involved and working with the pipeline integrity folks as like a multidisciplinary group. And then specifically, I just called out this Alberta Energy Regulator bulletin that is highlighting integrity management programs for pipeline operators. That is an imperative to consider slope movement to avoid those loss of containment events. So then specifically in the the interior plains, as I mentioned, there's high susceptibility to landslides. There's an expanded schematic here showing the pre-glacial river systems, just the high level general. It's quite a lot more dense than this. But the inset figure is showing us why these landslides are so pervasive and problematic in the prairies. So the bedrock sediments are Cretaceous aged, and the shales in particular are very weak and have bentonite seams, so montmorillonite that has a really low residual friction angle, can be 8 degrees or less, so it's really low strength. And so, and in here, as I mentioned too, is where the oil and gas reservoirs are too. So this is why it's so prevalent in the prairies, because we have pipelines in here. So the pre-glacial setting showing the Cretaceous sediments, then affected by a glacier coming over top and scouring down into, like, carving into these Cretaceous sediments, which are the shales are the things we're always concerned about as geotech. And then as a glacier retreated, these meltwaters come through and carved even steeper valley banks into these sediments. And because meltwater happened very fast, they're over steepened slopes. And because of the weakness of the shale, it starts to fail. And so landslides are forming on the valley banks. And so today's situation in a lot of these river systems in the prairies are quasi-stable landslides. So sitting factor safety around 1, and it doesn't take much to destabilize or to accelerate movement. So most of them are moving extremely slow. So on that sort of, 10 to 25 millimeters a year, but like a big rain event would be enough to accelerate that. And if your pipe is trenched in this kind of terrain, it will have an effect, a negative effect. So just another image showing the big types of landslides that are in the interior plains, which is also called the Western Canadian Sedimentary Basin. So they're translational to rotational. There can be spreads and then a compound version of that. So often a rotational upper component with translational near horizontal plane of movement that's often on a weak layer in the shales. And so showing the displacement versus time plot, like the first time failure for these slides would have happened post meltwater flood out with deglaciation. And then movements are just continuing on. And then these subsequent movements that can be episodic happen with time and are somewhat unpredictable. So it creates this whole situation that needs monitoring and maintenance and avoiding if we can in the for pipeline alignments. So Doug Dewar created a nice summary of landslide interaction with the pipeline, and so how the pipeline is configured across the landslide tells us how it could behave if the landslide continues to move and affects it. And so this categorizing system can help us just think about where the pinch points on the pipeline would be, what kind of mitigation measures could be used to either slow down the pipeline or beef up the strength of the pipe. So this is a helpful reference. And then a few words here, but would like to kind of go through this with everybody about how the landslide pipeline interaction approach should go. So it's a risk-based approach, so like a risk management type of way of dealing with these. So first of all, we identify the threat. And so remember, it matters whether the pipeline has not been installed and it's new and we have the opportunity to reroute and avoid, or if it is an installed pipeline and now there's an issue. So there is a difference with what tools you have available. But identifying that threat, so using mapping tools, field reconnaissance, geotechnical investigation, measures to figure out is really, we want to find out what that activity state is for the landslide. Like, is it moving? How fast is it moving? And how big is it? How deep is it? Those characterization kinds of things. And then assessing the consequence. So, you know, the extreme case is a loss of containment event. So that is the ultimate goal, but there are other consequences that could happen, and depending on the magnitude of the landslide, it's something to consider. And then likelihood as well, assessing that. So there's a large uncertainty in our ability to assess when, how likely a landslide is to move. And because especially in the prairies, it could be episodic. I think we're unable to have certainty with this, is with the landslide terrain. So then looking at what other tools we have available to further assess with monitoring. And the monitoring here is not a mitigation. It's to characterize the landslide and the pipeline behavior. So using change detection tools, we'll go through that a little bit more in the next slide. And then creating an engineering geological model. So that's an important outcome of this, is what is, the defining the landslide in plan and section, and where is it the ground moving, and what is the rate it's moving, and how is it interacting with the pipeline. So that feeds into a pipeline structural analysis where they're using finite element methods, incorporating that geological model data so that they can set thresholds of movement, thresholds to pipe strain, and there's this repeating loop process to monitor landslides. It's multidisciplinary. Communication is key. So once the geohazard has been identified as a high consequence landslide, then this kind of a scenario gets triggered. And then the ultimate goal is to reduce or eliminate the threat of the landslide interacting with the pipeline. So then having the operator ready with the plan and design at the time of monitoring, instead of waiting for thresholds to be met, is a better approach to risk manage the pipeline. So getting that in the process is pretty critical. So either considering how to slow or stop landslide movement. Lots of ways you can do that. It's so very case by case basis that it's the basics of you reduce the driving forces, increase the resistance. You can strengthen the pipe, move the pipe, so a reroute or an HDD, a trenchless solution, reducing the elastic strain on the pipe by stress relief. You can reduce product flow if things are getting a little critical. So if loss of containment happens, the impact isn't as massive, or completely shut in the line. So there's a whole bunch of options that can be considered. And so the point is these need to be addressed right when the threat is identified. And then once those have been, the threat has been mitigated, then there's monitoring for any residual threat. So it is an important approach, and some that needs educating sometimes with the owner. You know, if this is first time for them dealing with this situation. So just, you know, to understand this in our role is key. So looking at monitoring a little more holistically and using change detection with the various monitoring tools becomes a pretty critical piece of the puzzle here. So we can monitor the landslide by, you know, our conventional slope inclinometers. We can near real-time automate those with shape accelerators or in-place inclinometers. We can monitor groundwater levels, standpipes, or vibrating wire piezometers. We can use survey monuments or like near real-time monitor GPS units can be installed for the near surface movements and can be moved to characterize the whole pipeline, or sorry, the whole landslide. The site reconnaissance, so doing a walk over the slope periodically or at triggered events becomes an important thing. There's an art to this, and so it's not all just data coming back. Like, we're pulling in some important observations when we do the field walkover. And then the pipe itself too can be monitored by using inline inspection tools. And so they can be run down the pipeline, and it basically, like in a simplistic form, is like getting a slope inclinometer result out of the pipeline. So it's a super important tool, and the integrity team in the pipeline owner will be using these. And also the addressing the climate is really important, as I mentioned before. So having either a weather station at or near this landslide, or pulling weather station data from Government of Canada weather stations, and same with river level gauges. So seeing how big rain events or snow melt happens and the river levels increase, like when they increase and how much, and what is that doing to the behavior of the landslide, which then contributes to what's happening to the pipeline. So then up in the sky here, so drones can be used to collect images, as well as doing a LiDAR DEM image. Photogrammetry can be done. We can get satellite data for an INSAR, and there's just scads of tools is the point here. And there's no one fits all. It's kind of a combination and case by case basis. So it's something that needs to be considered case by case. And then, as I mentioned, setting variables for these monitoring tools is important too. Otherwise, like, what are you monitoring? You're monitoring what, right? Like, when do you raise the alarm? And so that's really important. And then that iteration through updating the models. So the geological model and the pipe structural model itself, and then reviewing the mitigation strategy. So it's this round and round iterative process to safeguard the pipeline. And the ultimate goal might be a reroute or a line lowering with an HDD that goes much deeper to avoid the landslide. But you know, those things take time to coordinate and get ready. So there may be a situation where this monitoring plan has to be in place. So I mentioned monitoring the pipeline as a really useful tool. It's called Inline Inspection Inertial Measurement Unit. So the, you know, in brackets, the pipeline inclinometer. So that gets completed by the operator. It provides evidence of pipeline interaction with landslide movement among a whole host of other things, but we're focusing here on the landslides. So it provides a measurement of the 3D geometry data of the pipeline. And then when you repeat these inspection runs, you can get change detection that will determine the bending strain experienced by the pipeline. So this becomes a really important monitoring tool with the geohazard and geotechnical monitoring. So the terrain mapping features can be screened out, where the ILI IMU can be zoned in on to assess bending strain. And so if the figure on the right, there's a landslide shown in cross-section. By taking a deep dive into this, the tool run data, we can see with successive tool runs the change that's happening in the strain, that we're getting sort of tension at the headscarp and compression at the toe of the landslide. And so it's showing that the landslide is moving. So even without slope inclinometers and all the other geotech tools, this tool will tell you if there's a landslide affecting the pipeline. And so it can be a really good screening tool to figure out like next steps, whether that's more geotech monitoring or initiating it, or another integrity option. And then looking at the configuration of the pipe running through this landslide. So if it's running parallel or oblique to it, will affect the bending strain and where it's happening on the pipe. So an understanding of that is required. So the intensile movement or axial strain that's under development with this tool, but it is coming. But this tool can measure compression. So for that parallel interaction, because we often will orient pipelines parallel along slopes. So finding the tension areas is coming. So the structural analysis, looking at finite element modeling with the pipe using, the pipe stress engineers doing this. So they essentially collect the data from us, preferably as a summary, and from our instruments and other observations that we're using to monitor the landslide. The ILI data is used. They require an engineering geological model that's showing what we are interpreting as landslide movement. And if it's complex, like in this case, where there's 3 blocks shown in cross section, and then there's also a mass shallower surface landslide happening here. So it's one of these big, complicated prairie valley slopes. And out of that comes the ground movement profile. So how much the ground is moving along the landslide is, in this case, these different blocks are moving at different rates, which complicates where the strain is being observed on the pipe and where prediction would be where the pipe would fail. So there's was a lot going on in this slope with stress relief and pipeline replacement. And so the forecasting of how long could this pipe remain in service had to be considered iteratively. And so that would be looking at these outputs from the modeling on the lower right. So at the this pipe was trenched in the slope, and then an HDD at the toe of the slope, which isn't recommended anymore. And to do an HDD at the toe of a landslide slope is you create an anchor point here. There were lots of reasons this happened in the past, and primarily was not recognizing landslides properly and limitations to trenchless equipment. So they couldn't do big, long drills. They could only do short ones early on. So in the outputs of this analysis, it's showing that there's a compression, there's a strain event that the landslide movement is just concentrating strain at this overbend, and the prediction of how much movement it could take was enough that we had to shut the pipeline in this case. So anyway, just to show the importance of modeling and outputs and predictions and thresholds and that scenario you can get into with landslide monitoring. Okay. So switching gears a bit to talk about trenchless crossings, is it's another place where pipeline operators spend a lot of money. So one of them is landslides for sure, and the second is crossings. So they are done, so trenchless crossings are done to avoid obstacles typically. So, you know, surface features that are in the way of a pipeline right away, such as a railway, roads, rivers, even like congested sites that would be just a real pain to open cut. This is particularly in urban areas, and then even like environmental or historical resource sensitive areas, we can, instead of open cut, we could bury the pipe with trenchless methods so that we don't disturb the ground surface. So lots of reasons you would use a trenchless crossing. There are some advantages over open cut, and I mentioned a few. So just reducing impacts on the environment, the social cost of, you know, people having to travel around an open cut construction. There's a big footprint with that. And then if you're crossing rivers, including the slopes, then you don't have to deal with trenching up slopes and the issues that can cause. There's less equipment needed, less personnel and fuel needed, so, you know, costs are affected by that, and then the surface restoration costs would be less. So the trade-off then is like, so from all the, we can bury the pipe and avoid obstacles, but you get into the underground space, which is where geotech engineers come in. So we need a proper subsurface assessment, and then picking which trenchless tool is the most feasible method to interact with the subsurface ground conditions is the goal. So there's uncertainty in underground construction. The tunneling industry over I guess since people have been tunneling have come across this, just unexpected conditions, and it leads to cost overruns and claims, and you know, and then at some of these obstacles, we can't even investigate the ground conditions below it. So like at a railway crossing, you can't drill a hole in the middle of the tracks to find out what's immediately under the tracks. And so there's some situations where you have to infer geology and rely on your desktop mapping abilities. And then at some point, you just have to accept some of the uncertainty as a risk to the project. So depending on the complexity of the crossing, the geotechnical investigation needs to be tailored for that. So if it's a short rail crossing that's 60 meters long, then, you know, 2 boreholes would be required. But if you have a over 2,000 meter river crossing, then that won't suffice. And then assessing the methods, as I mentioned, the ground, how is the ground going to behave relative to the trenchless method and the equipment that is used. And then out of that, we provide an input into feasibility, design and constructability of the method that's preferred, and if there's an alternate kind of method. So what does that look like for us? It's coming up with the terrain and the subsurface strata. So looking at in plan and profile again, just to make sure we understand the geological setting, where the hazards would be, coming up with geotechnical engineering material properties, and then classifying the ground behavior. They become really important inputs and things that we have to figure out. And then rivers, like showing these images here, they're already complex terrain environments. And so, performing a deeply buried crossing under these complex features requires a good understanding of geology. I have a comment here that geotechnical baseline reports may be useful. So they are used in the tunnel industry pretty pervasively and are being more and more adopted into these trenchless kind of utility and oil and gas scenarios. And in the not so much in directional drilling, but it is coming more. I've seen and been involved with more and more, but certainly in microtunnels, baseline reports are used, and they are essentially a risk management tool. So they're used by the owner and the contractor to just help deal with problematic soil conditions and avoid claims because of bad outcomes. So in our input also becomes a risk management tool. So we're identifying the hazards, assessing and mitigating them. Whatever can't be designed away to avoid often gets transferred to the contractor. And this is where they're using our information to develop bids and execution plans. And then depending on the complexity of the project, how that contract is arranged with the owner could vary. So I put this up here just as I've been talking about ground behavior here and there in the presentation, and in the trenchless world, there's a Tunnelman's ground classification. So it was originally proposed or developed by Terzaghi, and then Hauer in the 70s updated it, and it's just, I have highlighted here just ground classifications that just help us describe behavior of what we would expect in an open bore in a trenchless crossing. And it will really affect how the contractor approaches their means and methods for constructing a trenchless crossing. Depending on whether the ground is firm, you expect kind of good tunneling conditions. Raveling can be problematic if it's fast, and then squeezing, running, flowing, swelling. Like there's descriptions there, but it all should trigger in people's minds that there's some things to be overcome if you encounter these kinds of scenarios with the ground. So then looking at the methods themselves, geotech engineers aren't trained on what trenchless methods are in your classical education. There are a bunch of universities that do offer some of these courses now, because this is becoming more and more prevalent and something that we're all, as practitioners, I think, are more and more dealing with. So this understanding is important for us because of what we have to recommend in the end. Is the method feasible? And then what are the bad actors in the ground that the contractor should be aware of? So the methods listed here, we can think of them kind of as like displacement techniques. So pipe ramming, so hammering, drilling techniques, so horizontal directional drilling. So that is more like a rotary drill. If we're thinking geotechnical, like how we go and investigate the ground, there's methods broken up in trenchless world that we can kind of relate to just straight off the bat. So like pipe ramming's like, driving a pile. Directional drilling is like a mud rotary system on a drill rig. And then there's these hybrids that I'll get to in a sec. Then the pipe jacking techniques. So kind of microtunneling is that, where you're pushing against a frame. And then the tunneling technique. So they're using a tunnel boring machine with a cutter face to circulate, and then thrusting pipe behind it. And the hybrid technique, there's one that's called direct pipe. installation. It's a Heron-Connect trademark that blends directional drilling and microtunneling, and it's becoming more and more mainstream. And just a note that all of these methods can be used as a hybrid, and they're constantly evolving. So it's something, if you're involved in the industry, to stay abreast of. The contractors are always coming up with new refined tools to get the job done. So looking at the big three, so there's directional drilling, has a longer, deeper drill path typically. The microtunneling requires a shaft on each side with a straight shot to achieve the trenchless crossing. And then the hybrid is called direct steerable pipe thrusting, or the Heron-Connect trademark direct pipe. And it's a hybrid of the two. So it's instead of a shaft, it's a surface launched microtunnel that can be installed on a curve like an HDD, and it's thrust from the surface and then advanced. The microtunnel boring machine is advanced and steered along a curve. So there's advantages, disadvantages of each. And these big three that I call them are the more expensive types of trenchless methods, and they have different ground conditions that they perform better in and not, and so those are somewhat listed here. We have three other methods. I just quickly highlight the horizontal auger bore, a pipe ramming, and then a down the hole hammer. And so these are all launched from a pit, so it could be excavated, shoring, a small shaft. And then the depth of cover can be pretty low on these. They're typically used for roads and railways. They're shorter than a typical HDD, so their maximum limits are like 60 meters for pipe ramming, and then 100 or so for the auger bore and down the hole hammer. And then ground conditions, so the selection is based on what we encounter in our geotech investigation and how the methods will perform in these scenarios. So like pipe ramming does not perform well in clay soils or bedrock, but it's really good in gravelly soils, where other methods don't work well in sort of gravelly soils or clays. So anyway, you need to just sort of understand both of them here, and I'm accelerating my pace here, so please bear with me. So the considerations to these crossings is our geotechnical investigation is a risk management tool, so we need to be characterizing subsurface properties and evaluating ground behavior. We definitely need an understanding of geology and then the variation of that materials through the terrain that we're working through, and then communicating those hazards to stakeholders. And then, as Gould said in '95, surprises are inevitable. So we're always going to have unexpected ground conditions that neither the owner or design team can completely eliminate from complex underground projects. So my last slide, a path forward in pipeline geotechnique. Pipelines are going to continue to play a key role in energy products and utilities needed for everyday life. New installations and safeguarding existing pipelines are going to continue to challenge geotechnical specialists for careers to come. And finally, innovations in energy products, remote sensing and monitoring tools, and construction techniques are just going to constantly improve, that are going to provide exciting work environment for people that are lifelong learners. So you'll have a good future in pipelines if you adopt it into your career. So thank you, everybody, for the time today. And I think there's a minute for some questions here. I do have a reference list up as well.